This is part 3 of a video lecture on circuit analysis. So in the last lecture, I was telling you all guys how the circuit that you're looking at right now is really the same as the circuit over here. So why is this circuit the same? So this is the same circuit, and I have traced out my currents, and I have my I2 in only one spot. It's right here. Well, here's the deal. I don't even need to have it over there. I can get rid of I2 altogether. This is how I would do this. I would erase this a little bit, and I would draw my branches. Here's my R5, here's my R6, and I can curve the wire all the way into this node. And here's my other branch, here's my node where it splits up, here's my R7, here's my R8, here's my R9, and I'm gonna curve it around and go it back into the node. So now you can see that all of my parallel branches actually start together in one node and end together in the other node. And this is really the conditions for being parallel. Your branches are parallel if they all start in one node together and all terminate in a different node together. That's what it means to be parallel. Now, this can be a little confusing in a case like this because you have 4 nodes, right? And they don't all start in the same node. But here's the deal. You can merge your nodes if you don't have any circuit elements in between them. So, let me put this somewhere over here. You can merge your nodes if you don't have between them. And I really don't in this case. My I2 serves no purpose. The only purpose of I2 is to stretch out my circuit so I don't have this diagonal line. But it doesn't really matter. Okay? The I2 doesn't matter. I can get rid of it. So I can merge these 2 nodes, and yes, I would end up with a diagram that looks like this, and it's ugly, right? But we can clearly see that all of my parallel branches start up in one node and then end up together in a different node. So let me put this up as well. Circuit branches are parallel if they start together in the same node and terminate also together in a different node. So my personal favorite way of thinking about this is a river. So here's a river. I'm going to draw it. And it's not going to look pretty, but I'm going to draw it. So here you got a river. And then all of a sudden it splits up 3 ways. But then, all of a sudden, it merges together. So over here, I have my branches, right? I have 1, 2, 3 branches, right? This was my start node. And this is my end node. And when you think of your parallel circuits in this way, it actually does become very, very obvious what is parallel and what really isn't. So, let's extract an expression for what is actually parallel in this circuit. And I already told you what it was, right? I told you that it's R4 parallel R5 plus R6 parallel R7 plus R8 plus R9. So I'm gonna put down everything in this bubble in the big expression below. So parallel is R4 parallel in parentheses R5 plus R6, and this is all parallel R7 plus R8 plus R9. Okay, very straightforward. All right. Well, I can now make an equivalent circuit that will be exactly in series. If I were to replace my red bubble with one big resistor, or one small resistor in this case, since this is a parallel circuit, I'm going to end up in a circuit that has only resistors in series. So here's my equivalent circuit. And I'm just going to hand draw it, so hopefully it's not going to look too horrible. So this is R1, R2, this is my R equivalent, and this is my R3. Okay, well, this circuit is extremely easy. This circuit is extremely easy to calculate total resistance, right? Our total is just R1 plus R2 plus R equivalent plus R3. And I have 1K everywhere, right? Okay. So the only question is, what is R equivalent? Well, if you guys remember, we had this whole big expression over here. And I can definitely extract R equivalent from this expression. This is a parallel expression, so once again, I'm going to have 1 over R equivalent equals 1 over first term, R4, plus 1 over second term, R5 plus R6, plus 1 over my last term, and this one's big, right? This is R7 plus R8 plus R9, right? But ultimately, in the end, this is it. And this really isn't so bad. So next, I need to plug in some numbers. Let's see, this is going to be 1 over 1,000 plus 1 over 2,000, because they're all 1K, right? And I have 2 of them, plus 1 over 3,000. Okay, this is where you grab your calculator and you start doing calculation. 1 over 1,000 is 0.001. 1 over 2,000 is 0.0005 plus 1 over 3,000 is 0.0003. So in the end, you're going to end up with a number that is 0.0018, right? Okay, you're still not done, right? I still need to find R equivalent. Now my R equivalent is 1 over that answer. And guys, seriously, use a calculator. There is absolutely no need to torture yourself by trying to do this on paper or in your head or anything like this. And this comes out to 556 ohms. Okay, so now that I have R equivalent, I can go back to this formula. I can plug in a few things, and I have 1K, right? That's 1,000 plus 1,000 plus 556 plus 1,000. So this comes out to 3,556 ohms. And of course, please put this in engineering notation. So this is 3.56. I'm rounding this up as I'm writing this down, K ohms, like that. So it took me a while to get through this problem, but that's because I was giving you a bunch of definitions and explaining you a few things. Once you know everything about the nodes, once you know what it means to be in series and parallel, this method is actually very quick, even for quite large circuits like this one. The circuit is not small, right? So I hope the lecture was helpful, and the assignment, and there is assignment on the hub attached to it. The due date for that assignment is Monday morning, 8 a.m. Okay, that's Monday. Let me look at the calendar. That's Monday, January 14th. So make sure you actually do it on time. Thank you.